This is the first discussion of file systems. Maybe not the very first one, because remember we did talk a little bit about file systems in the first week of CS124, but now we're going to talk about them in earnest because you're going to have to update the Pintos file system, and therefore you will need to understand how it works. So we're going to start talking a little bit about the concepts underlying file systems. And of course, the fundamental thing that we notice with computers is that programs need persistent storage of one form or another. It's just absolutely inescapable because you don't want to type the program in every single time. And so we need a way of saying, here are the program instructions. And whether that be punch cards or a little USB drive or a solid state drive or a hard disk or whatever it is. But there's a lot of other things that we'd like to not have to say every single time as well. And so that would include configuration files, photos of our dogs, whatever kinds of things. We'd like to be able to save these things so that we don't have to keep regenerating them all the time. And so persistent storage is sort of an essential component nowadays of how we do computation. We also have this other issue to be aware of, which is that software fails and hardware fails. Both of those things fail. And we'd like to make sure that we have some kind of storage mechanism that persists through failures, at least to the best of our ability. It may be that if a hardware failure occurs, my wife had a solid state drive on her laptop that failed, and solid state drives are pretty nasty when they fail because they don't fail incrementally. They fail all at once, and so you lose all your data all at once, which is why backing up becomes even more important when you have solid state drives. But so there are mechanisms we can use to make failures less severe, and a lot of them involve properly and carefully managing persistent storage. Okay, so there's a lot of different forms. If I were to ask you for some examples, you'd probably come up with these, and I don't know if you would come up with others. Hard disks becoming much less common unless you have a big server machine. You'd have hard disks. Our network attached storage server definitely has 5 hard disks in it because having 5 solid state drives wouldn't be as cost effective, and they would be a lot less storage. Solid state drives, USB flash drives, flash memory cards. You might still see tape drives. They're still used rather frequently for backing up. Optical drives as well can often be used for backing up. Okay. Sometimes you have data sets too. I mean, there's a lot of reasons why we like this external storage. Another one is that sometimes you can't get a computer with the amount of DRAM you need to hold the entire data set you want to process. Even though like this laptop has 32 gigs of DRAM, what if I want to process a 1 terabyte data set? Well, coming up with a computer with 1 terabyte of memory, I suppose, is possible, but not common, not easy for me to get access to anyway. So being able to manage a large data set on an external device allows me to do computations I wouldn't be able to do if those devices didn't exist. Okay, so also we have situations where we may want to share information across multiple processes. Maybe I want different processes to access and manipulate the data at the same time. This is very common in the way database systems work. I've got my set of data files, and I may have multiple processes handling different clients interacting with that data all at the same time. The one issue with persistent storage is, at least right now, it's way slower than any of the other kinds of storage we have on our computers, DRAM in particular. But then you get into static RAM, which is used for the caches, the hardware caches, and that stuff is blisteringly fast compared to even DRAM. But you've heard me say this throughout the term more than once, quite a few times. Hopefully you have these numbers memorized yourself. But if an instruction takes 1 to 3 clocks, a level 1 cache or a level 2 cache memory access is going to be on the order of 10 clocks. So level 1, maybe you have 1 to 3 clocks. Level 2 is going to be 10 to 20 clocks. Level 3 might be 20 to 50 clocks. Then you start getting to your main memory. That's going to be anywhere from 50 to 200 clocks. We usually estimate it as 100 clocks. And then you get to your storage device. Solid state drive is going to be on the order of 100,000 clocks. And the hard disk is going to be on the order of tens of millions of clocks. Really slow. So we want to talk to them as little as possible. That's obviously the goal here. As I say on the slide, reading 1 byte, you've got that huge latency of talking to the device. But when you read 1,000 bytes or 10,000 bytes that are next to the 1 byte that you started reading, that's incrementally not much more expensive. So we might as well read and write blocks of data off of these large devices. And that way you sort of get the amortized cost because you're pulling a whole block off or you're pushing a whole block back to the device. These fixed size blocks are typically governed by the storage device itself for a long time, starting back in the 5.25, or I should actually say 8-inch floppy disks, 5.25-inch floppy disks, and then 3.5-inch floppy disks. Those would have sectors of 512 bytes, and all of you are probably painfully aware now that virtual memory has block sizes of 4 kilobytes, and so those tend to be the sizes that govern moving data back and forth with these devices. Modern hard disks and solid state drives are also moving to a 4 kilobyte sector size because it plays really well with the virtual memory system. We don't want to have to think about this. It's infrequent that an application wants to talk to the block device directly. There are a few kinds of systems that do. Databases are about the only one where it's really well justified, but a good database server may have the ability to talk to a block device directly and not use the file system. But most of the time we like having some kind of abstractions that steer us around a lot of the difficulties that arise with persistent storage. There are things applications don't want to have to think about. I mentioned different block sizes, different ways of reading and writing the devices. Like, we haven't even talked about read, write, and erase characteristics yet. In the future, we'll talk about solid state devices and hard disks and how differently they behave. Hard disks support in-place modification of data. Solid state drives do not support in-place modification of data. They have these weird rules they follow. And so that has a massive impact on the optimal way of interacting with the device. It'd be really nice if the OS took care of that, and then your application can just pretend everything is normal. Applications also don't want to deal with keeping track of bad sectors, detecting bad sectors, which is a pain all by itself, trying to recover from bad sectors that have just been detected, remembering where data sets start, or where they exist. Are they contiguous or are they not contiguous on the storage device? So basically what the OS presents is this abstraction we all know as files. And this may be something that you never really appreciated, but you will definitely appreciate it after Project 5 when you have to interact with how a file is laid out on a file system. So a file is basically a single logical unit of data. I have a file, it has a bunch of data that all should be grouped together in some way. And as I say on the slide, this is a contiguous linear sequence of bytes. So it has a first byte and then a second byte and then a third byte and so forth. And I can typically read, normally the way that operating systems present this file abstraction is I can read a stream of bytes out of this file until I hit the end of the file. I can extend the file, I can truncate the file, do various operations on it as well. Okay, so the file system is the part of the operating system that manages and exposes the file abstraction. Another thing that you should be super happy about, and you probably had no idea that this thing was even real, but you should be very happy that modern operating systems really don't constrain your file's contents to follow any particular format. maybe the worst constraint you have to live with is that bytes have 8 bits in them. Old computers and then also modern digital signal processors often would have different numbers of bits in the values that they would work with. But thankfully, everybody sort of settled down to having 8-bit bytes. And so everything is sort of very straightforward to interact with. But it used to be that because of the hardware you were working with, you had constraints on the nature of the file data you were allowed to represent. Okay. Yeah, so like I say, the OS may distinguish between text and binary files. Why would that be? Well, many of you encountered this term if you were working on a Windows host platform and using this Linux virtual machine inside Windows, and you notice that the text file would have character return new line, and Linux was expecting it to just be new line, and it was frustrating. Well, binary files are even worse because it may have new line characters in it, and it may have carriage returns in it, but those should not be interpreted in text. They should be interpreted as binary. And so that's why operating systems often will distinguish between text mode and binary mode if it's trying to do any sophisticated translation or interpretation of new line characters in text files. Blah, it's terrible. This is why I wish everybody would just do it one way. But unfortunately, we live in the world we live in. So yeah, you may have situations where files are constrained to follow specific formats. Well, you're all familiar with this. The binary executable format on Linux is ELF. If you're running Wine, you can also use portable executables. If you are on Windows, Windows is getting clever enough to be able to use some Linux ELF formats as well. So we're getting more and more sophisticated. But as I was mentioning, the storage device used to constrain people. It used to be if you had like your punch cards, you could only have 7-bit bytes. And so you would have, that's why like you'd have characters 0 through 127, and these were the files that were used for, or the character set that was used for specifying programs. You were just constrained. And you could have 80 character wide text files, and that was it. And you could output up to 132 character files, and that was it, or character wide lines. So because the devices just weren't any more clever. But thankfully, we have very sophisticated input and output now on computers, so we can do basically whatever we want. Now, there's also another kind of circumstance you may run into, which is an operating system that is purpose-built. And I want you to think of something like your camera, your digital camera, which knows how to write just a couple kinds of files. It knows how to write image files, and it knows how to write metadata files for your images. Maybe it knows how to write movies, and that's it. So in a purpose-built operating system, it may only understand a few different file types as opposed to being very general purpose, like our, desktop and laptop computers that we use. Now, files are assigned a name. This is a review, I'm sure, for all of you, but files will have a file name that basically hopefully indicates something about what the contents of the file are, how they're relevant to the user. And you oftentimes also have an extension which says this is the kind of file that you're working with. So a JPEG image might have an extension of .jpg, or a PNG image will have .png. Now, good software doesn't trust the extension because users get confused sometimes. And they'll say, oh, all my images are supposed to end with JPG. And so they put JPG at the end of a GIF image, or they may put it at the end of a TIFF image or something like that. And so good programs will actually try to identify the file based on its contents as opposed to by its extension. But this used to be very common in sort of olden days, like back in MS-DOS and early Windows, that the extension was the trusted indicator of the file's type. Some of you may be familiar with this program. There's a program called File, and you can type file space and then some file on your computer, and it will try to identify the format of that file based on inspection of the file's contents. And this is actually also available through a library that understands the formats or the indicators of many different formats. Okay, the portion before the extension is often called the base name, and there are actually utilities on Linux and Unix, dir name, base name, and so forth that will allow you to get the different parts of a file name, pull them out. And so, yeah, the term file name may refer to either just the base name or the base name and the extension. It really depends on the context, unfortunately. And then, of course, you also have path, which may include just the file name, or it may include the file name plus any directories to reference the file from different places in the file system. And then, yeah, like I say, the constraints on file names vary from operating system to operating system. It's really wild. There's been a lot of different variations over the years, and now you can actually use Unicode and file names and so forth on many different platforms. Capitalization is another source of many headaches. Some OSs require capitalization to be respected when you're referring to a file. Some will preserve the capitalization that you type, but they will treat differences in capitalization as referring to the same file. So it just really depends on the nature of the operating system. DOS, Windows, and Mac OS, if I remember correctly, well, not DOS, but Windows and Mac OS will preserve the capitalization you specify, but accessing a file via other than the file's capitalization will still result in accessing that file. Linux and Linux in particular respects capitalization. Okay, once you have more than just a few files, remember that the initial Pintos version starts out with everything in a single directory. So once you start having more than just a few files, it becomes really nice to be able to organize them in some useful way. And so we tend to have directories or folders that allow us to group files together. Just like if you had a file, like I have my filing stuff right here, and I have a folder, and so I can put papers inside here. And so it's just kind of the same idea, except on a computer, I can nest them almost arbitrarily deep as well. So so within a specific directory, every file has to have a unique name. Two different directories can contain files with the same name. There typically is one place in the file system that's considered the root, or the top level of the directory hierarchy. Some computers support multiple roots depending on the way the file system is exposed by the operating system. So Windows and MS-DOS before it had this notion of each drive or each partition was a root. So you'd have C:, D:, E:, F:, and so forth. Unix operating systems tend to expose everything off of a single root that's just called /, which probably many of you are aware of. So, but the root directory will be a starting point in navigating the file system. Okay. Oh yeah, and I wanted to mention this because this is kind of an important and an interesting one. If the file system doesn't have a root directory, programs must know by themselves how to find files. So they have to actually be able to go and track down where a file is stored by just looking at the disk contents. That seems like a terrible thing to have to do. So this is why basically all operating systems provide an abstraction for this. A few examples, you'll have simple operating systems that support maybe just a single level or a two-level file system structure. And so you'll have, for example, a single level directory where the root just contains files. It can't contain any subdirectories. This is how Pintos starts out. Files within the directory must be uniquely named. And so one of the extensions of this concept that you frequently see is when you move to multi-user systems, you'll see a two-level file system structure, because you'll have one which is the root, and then each user can have its own directory. to store the files of that user. And so you'll oftentimes see that kind of structure. This happened pretty quickly on Unixes because Unix has been a multi-user operating system for quite some time. Okay, but the way we do it now is something far more sophisticated. We'll actually just have a graph that somehow specifies how files and directories may be linked together. And you'll notice here that there is a root to the graph. So we have root, but it is a graph, and it's not even nice enough to be a directed acyclic graph. It is absolutely possible to create cycles in a file system where you start at the root and you descend down some series of folders, and you find that you descend forever because one of the folders contains a link back to an earlier folder in the hierarchy, and you can just keep following that loop as much as you want. And this would sometimes generate mayhem because if you have something like tar or some backup software and it's just following links through the file system without being clever, it may enter into an infinite cycle and get stuck. And that's always hilarious. So, but yeah, this is what generally operating systems provide now, is a graph for your file system. Okay, so files will be referenced by specifying a path from the root to the file or the directory you want to reference. So root, like I said, on Linux or Unix will be a slash, so you might have /home/user2/d or /home/user2/c, something like that. And so you have different kinds of separators you need. Like, how do you separate directory names? Well, you can see that operating systems have chosen many different options over the years. Windows tends to use / and Unix tends to use /. You may also have a list of directory paths that, if you want to set up your system path, or if you're doing a lot of Java programming, your class path. And again, OSs do these things differently. I'm trying to remember. I believe Windows uses semicolon because colon can be used in C:// blah, blah, blah. So Windows will use semicolon for path separator, and Unix will use colon for path separator. So, it's frustrating. And this is why a lot of programming languages like Java and Python support some mechanism for figuring out the platform specific separators to use. It's just like, why does life have to be so complicated? Okay, every process has a current directory. This is something that you'll actually have to implement in Pintos. The current directory allows you to do relative accesses to the file system instead of always having to specify an absolute path. And you all see this when you work at a command shell, because your current directory will be the directory that your file system operations are relative to. If you want to start a program, / program name. If you want to change directories, it can either be an absolute path or a relative path compared to where you are right now. Okay, yeah, dot will be the current directory, .. will be the parent, and that tends to be all it is. So you can say .. if you want to be silly. You can say .. and you'll drop down a couple of levels in your hierarchy. Okay. And this also allows you to share files. And we used to do this kind of thing on the CS cluster a lot for classes, where basically you could work with other students' files, or a teacher could grab students' submissions out of their own local directories by just doing relative accesses or absolute accesses if it was necessary. Okay. So you have a lot of different options you can use for that. Sometimes we don't want to share files with other users. Like if I'm the teacher and I'm grabbing student submissions to grade, it would be a FERPA violation for me to share graded work with other students. And it would also be, unfortunately, a FERPA violation if I was careless and allowed other students to access the graded work. So in these kinds of situations, you can actually specify permissions. Many file systems have this metadata mechanism, and the kind of mechanism varies from OS to OS, but they basically allow you to say, these are some more details about the file, like the file permissions. Read, write, and execute tend to be the Unix permissions. Windows has a bunch of other permissions as well. And so, yeah, here's some of the details you might see in the metadata for a file. User that created it, when the file was created, when it was last modified. Both of those timestamps tend to be recorded by the operating system implementation. Access permissions. Are you allowed to run this thing? Are you allowed to write to it? The icon associated with the file, like Mac OS is very focused on being a usable operating system. So the icon associated with the file, you can have colors, you can have tags, you can have all kinds of other details in the metadata for the file. And most operating systems also allow you to specify the application to use so that you can double click on a file and the OS will automatically start the appropriate type of program to let you work with that file. You know, like your JPEGs on a Mac, you double click on a JPEG and it'll open up in preview or something like that. Files can be shared between different directories in a couple of different ways. You may have noticed this if you are looking carefully at the picture that I have here, that this file is named C and it's linked from two different locations. And linking is exactly what we call this. A link is basically like a pointer on the file system to a file that may reside in a different directory. Now, there's two different ways that you can link to a file. Because if you think about the way the file system works, you've got this platter, or let's say you've got a row of chips if you're talking about a solid state device. But either way, you have a sea of bytes. And you have the contents of the file itself, the actual file's data. And then you have something saying, this is the file. And we call that a directory entry. So the directory entry and the file's contents are almost always kept separate from each other. And if we do that, then we can definitely have multiple directory entries that reference the same file contents. And so when we have that, we call it a hard link, because it basically looks like the file is in this directory. And it also looks like the same file is in another directory. That's just the way that the file system is laid out. Okay, but we can also have another kind of link called a symbolic link. Sometimes you'll hear it called a soft link. And the symbolic link is basically a file in that directory, but really the file says, I really mean this other file. And so that's the way that that situation works. A really interesting looking bird just flew by. I got distracted. There's some really interesting birds in our backyard. So in this example that I have in the picture down below, you can see that this home user1 BC file would actually be a separate file, and the contents of the file would say, actually, you should go look at home user2C. Okay, so that's the way that symbolic links work. And since not every file system supports hard links, Windows didn't support hard links for a really long time in its file systems, so it would use symbolic links. And so you might have seen, if you have used Windows for a really long time, when you create a link or a shortcut, those kinds of things, it creates a little .lnk file that references the other file. And the file system implementation knows how to take those symbolic links and follow them to get to the file that's actually referenced. Hard links are simpler. You just open the thing and it is the file data. Okay, how are these things stored? Files are given this abstraction that it's an unstructured sequence of bytes. It's a contiguous sequence of bytes, and the program gets to say what the sequence of bytes means. The program has a couple of options. It can either read in the sequence of bytes as just a stream of data. It can write out a sequence of bytes as a stream of data, or it can actually seek within that sequence of bytes as well. So this is the abstraction that the OS presents and that applications take advantage of. Let me say here, operations on files: create a file at a specific path, delete a file at a path, rename a file, truncate. I mentioned truncating or extending a file. And when an application is reading or writing the file, the OS maintains a position. And on Unix, it's exposed. You can modify the position using an lseek operation to move forward or backward. It tends that you can do it relative to the start of the file, the end of the file, or you can have relative to the current position as well. And so this allows a program to treat the file's contents however it wants. Okay. And of course, if multiple processes have a given file open, that means that each process has its own current position, because otherwise that would be crazy. Now, when you have programs interacting with a file, it could do a couple of different things. One, as I was describing just a minute ago, you can just stream the contents out of the file into the program. Or you can seek to a specific location, read a chunk of data, or write a chunk of data, seek to another location, read or write a chunk of data. So we call these sequential access and direct access, or relative access, or sometimes you'll hear it called random access. So you have these different kinds of access that can be performed. And so here's what I want you to think about. This is the reason why I'm telling you this. We have these program behaviors, and the offset that a program may specify is from the start of the file. Now, what does the OS have to do? The OS has to take that logical offset from the start of the file, and it's got to figure out what sector on the device that logical offset corresponds to. So when the program says, I want the next 20 bytes based on the current offset, the OS has to go and look at the file system and say, that's in sector 936. And so it pulls sector 936 into memory, and then it hands the program the appropriate bytes from that sector. So we have a complicated mapping problem of mapping these logical offsets in files to sectors so that we can do these operations. Yeah, and so you'll have layouts that are very good for sequential access. It makes it very easy to chase through, but the problem is they're terrible at direct access, like just taking an arbitrary offset and figuring out what sector it corresponds to. Okay, some layouts are really good for direct access, and they may have other negative characteristics. So this is the challenge of designing a file system implementation, is figuring out the way of balancing both sequential access and direct access. Now there's one other problem, which is that you also have to take the storage device's capabilities into the picture. So if you have a storage device, like a tape drive, direct access will always be terrible, because tapes are really good for reading sequentially, and they're terrible for doing seeks on. Whereas a solid state drive, which has no mechanical moving parts, is really good for seeks. And so solid state drives can do either sequential access or direct access really efficiently. So hopefully you're starting to get a sense of like the challenges of implementing a file system. You've got to take the storage device characteristics and the usage patterns into account to try to design a file system that can support programs effectively. Okay, so we'll start chasing through a few of these. I'll try to hustle because they're just too exciting to talk about, and I get distracted. But yeah, since we have large persistent storage devices, we can hold many files at once, and we access these things by blocks, sectors typically, so 512 byte sectors, 4 kilobyte sectors, depending on the recency of the device construction. And so the file system has to keep track of which blocks hold which parts of which files. And a really simple approach is to have directory entries which say, this is where the file starts, this is the block number of the storage device block where the file starts, and it has this many blocks, and that's all we record. So we call that contiguous allocation. Okay, so we have where it starts, how many blocks in the file, How do we do sequential access? Well, it doesn't really matter whether it's sequential or direct access or random access. We just take the offset, we divide that offset by the block size, because that'll tell us what block we're on, and then we just add the block start, and that gives us the block to access. That's all there is to it. It's really simple. So we just do a very simple bit of arithmetic to get to the block that we need to read. So contiguous allocation sounds great, but it has a bunch of huge problems. One is that we have external fragmentation again, because you say, I need 35 blocks this time. And then somebody says, I need 21 blocks, and I need 4 blocks, and I need 38 blocks. And then stuff gets deleted, and now you have a bunch of space spread out amongst all these files. And so you have to kind of like compact and deal with that kind of stuff. So external fragmentation is a big issue with contiguous allocation. So you can compact. Unfortunately, if you're compacting the storage device, you oftentimes can't have anybody using the storage device at the same time. And so you may have an operating system that has to do some kind of background processing to compact the disk contents so that you can free up this space that's sort of sprinkled throughout the storage device. Okay. The other issue you have is that extending a file's contents is a really common pattern in program behavior. And if you allocate a contiguous region and then somebody else allocates another contiguous region, and then you need to extend the size of the first file, you're stuck. You have to basically copy that somewhere else and get more space at the end. So what you can do, a simple tweak, is to just chain together contiguous regions, and we call that extents. So you have an extent, which is a contiguous run of sectors or blocks, and then you chain these extents together to store the entire file, okay? And so that dramatically reduces the external fragmentation issues because you just collect a bunch of extents to hold the file. Now, this is how old DOS and old Windows would work. You can see that you start to have another problem because a file's contents may be scattered still across the entire device. And if you're doing a sequential read, you may be hopping all over the device to do those reads. And if you're stuck with old technology like a tape or a hard disk, then you're going to be incurring a lot of seek overhead. And so we call the issue pertaining to that data fragmentation, because if the physical order of the file doesn't match the logical order of the file, then you're going to have a very slow interaction with the device. Solid-state drives don't suffer from data fragmentation because there's no seek overhead, but anything with seek overhead can have this data fragmentation issue. Okay, so as I say here, CDs, DVDs, and tapes all use contiguous allocation. CDDs, can't even talk right now. Optical drives, I'll just say it that way. Optical devices have a very interesting storage format that does all contiguous allocation. And a lot of times, like, they will actually support modification even though a CD may be read-only, you know, or you can burn it, but you can't reburn the same space again, by having entries that basically say, I made a file. And then later on, you'll have another entry that says, I deleted the file. And the OS just scans through all those things and says, okay, this file, even though it's on the CD, I'm supposed to present that it's not present because something later says the user decided to delete it. So there's some interesting characteristics of how those file systems work. Okay, linked allocation. This is starting to get a little bit more sophisticated. Basically, what we do is we link together a series of blocks. I'm getting ahead of myself. The storage device is chopped up into blocks, so maybe sectors, maybe something larger than sectors, multiples of sectors. And each block points to the next block in the sequence for a file. And so when you have a directory entry, it says this is where it starts, and this is where it ends, so that you know you've reached the end of the file, and you don't just have some weird like garbage value at the end of the block and you follow it dumbly and end up in la la land. So you have a starting block and an ending block. The problem with this is, how do you do direct access? If I have an offset that's like 200,000 and I want to figure out what physical block 200,000 corresponds to, I've got to chase through this list, counting off blocks until I find the block that I'm looking for. So sequential access, great. Suffers from data fragmentation, terrible for direct access. Hopefully everybody understands that. Compaction is not necessary, so we no longer have external fragmentation because we're always handing out allocations of space in the same unit size. And when you have allocations that are always the same unit size, fragmentation, I should say external fragmentation, goes away as a problem. You do have internal fragmentation though, because if you have a large block, you can only hand out large blocks, and you want to store small files, then you start to waste space every time you do a file initialization or a file allocation. Okay, yes, and data fragmentation, like I said, if the logical ordering of the file doesn't correspond to the physical ordering of the file, and the device has a seek overhead, you are sad with this kind of approach. It's going to be slow. Now, there is a small amount of space that's lost within each block due to the information saying when the next, where the next block resides. And you have to remember that hardware and programmers both like powers of 2, like a lot. And so if you're chopping off a little bit of each block, then you're going to start running into some difficulties over time. And so this is why this is an unappealing approach. A simple variation of this problem resolves a number of big issues. And so this is probably one of the big contributions of DOS, is this notion of a file allocation table. The file allocation table is basically the linkage information factored out of the file data. And so instead of having something like this, where each block knows where its next block is, you have a table which says, what's the next block for any given block? That would be a nice, easy way of describing it. So you can see here, I guess I started numbering from 1, so please forgive me for my trespass. So block 1, block 2, block 3. And so the entry in the file allocation table for block 3 would say, what's the next block? Now, in the old one, we had 3 pointed to 4, 4 pointed to 5, 6, 7, 8, 9, 10. So 4 pointed to 10. And so that's what you see in the file allocation table here. The file starts at block 3. The next block for 3 is 4. The next block for block 4 is 10. You come over here, and you basically can chase through the file allocation table to see what blocks form the sequence of the file. Okay, so that's a file allocation table. Now, the file allocation table could be large for large storage devices. And so it tends to be that these things are fixed size. And it tends to be based on the size of the entries in the file allocation table, which may be why you've heard of FAT32. Or if you were talking about super olden days, like when I started working with computers, it would be FAT8. Each file allocation table entry is that many bits, okay? So yeah, you have these problems. One is sometimes a set of FAT entries can't address the number of blocks the device actually has. So, old disks would only have, like, I'm trying to remember, they had 9 sectors per cylinder, and they might have 40 cylinders. So let me try to do some math in my head really quick. That's like 280 sectors, something like that. Some of them wouldn't be accessible. And so you could get away with an 8-bit file allocation table entry, okay? But quickly devices grew, and you would have many more sectors than file allocation table entries. And also, so this is basically what I was saying. FAT8 could only have 256 blocks participating in files. And so FAT32 has 4 bytes per FAT entry. So you can imagine the table itself is much larger, but it can also deal with much larger devices. So to deal with this problem, and this started pretty early on, this is something that Windows would start to do, is instead of having a file allocation table entry correspond to a sector, it would correspond to a cluster or a fixed size group of sectors. And so a cluster, as I say here on the slide, might be 16 blocks. And so this is the second problem that you would run into, is internal fragmentation. Because if you're doing FAT8, you have 256 entries, and you have a very large device with a lot of sectors. Now you're handing out allocation chunks in very large cluster sizes. And so you create your little 10-byte file, and you lose 64 kilobytes off your device or more. And so this became really irritating really fast. So clusters can be as large as 32 kilobytes or 64 kilobytes in size. And so that means that the file system can only hand out blocks of that chunk size. And that gets pretty wasteful pretty fast. Okay, so you have a 3 kilobyte file, 13 kilobytes is wasted. If you create a 100-byte file, then you have basically a completely empty cluster. I remember seeing this as a youth and being very befuddled as to why so much of my disk space would disappear when I'd write my little programs, because my programs weren't very long or very large, but nonetheless, it was allocating file space in clusters. So this was a problem. Let's see, is there anything else there's something else I feel like telling you guys about this, but I can't remember. It's probably for the best. Okay, indexed allocation is basically where it is when you want to design a good operating system these days. There's a lot of different indexing mechanisms that are used, and the approach is just fantastic, and most operating systems will use some kind of indexed allocation mechanism. Unless you're talking about, like, you know, I've got a little, this actually happens to be a little flash memory card. It's actually a micro SD card. This is for my drone. If I ever learn how to fly it, because we're pretty close to the Almaty airport, and the drone's always complaining about airplanes going by. But this will use a FAT file format, like exFAT or FAT32. You'll see it on these removable devices because it's easy to support, and so it'll be supported across a lot of different operating systems. But the file system itself on the storage device, like the one built into the computer, will use indexed allocation. And so the file uses some kind of index, typically a B-tree type index, my favorite data structure in the universe. And so basically you can think of it as each file has its own file allocation table that's optimized for direct access and sequential access at the same time. And you'll notice that the way that this is stored is the directory entry will point to a particular block that contains the index, and the index knows how to talk to the rest of the file. So the directory entry gets super simple. The index is where all the sophistication is. And so maybe you've heard of this thing called an inode. That's the index block for the file. And so you can see here that the index block will say block 3, block 4, block 10, block 13. And it's basically saying these are the blocks in the file that comprise the file and the ordering that they appear in the file. Okay, so direct and sequential access are very fast. It's easy to translate a logical position into the disk block. So you just take the logical position, you use it to look up the index in the index node, and then you use the block number to pull the actual block from the device. Easy peasy, super simple. Okay, the other nice thing about this is that we can store metadata in the index block, because almost always these indexes are super sophisticated. You tend to have many small files and then a smaller number of large files, but you still need to support both of them efficiently. And so since we have file systems where we can do hard linking, you start to think about the fact like, oh, I could have a directory that calls this thing one file name and another directory that calls this thing a different file name, and I might have different permissions, or maybe I have the same permissions, you start to run into this issue of where do you store the metadata? And so an easy solution is to just stuff the metadata into the index block for the file so that it's always in one place, no matter how many hard links there are to the file. So you don't get into some really weird scenario where this file is not executable or read-only from one directory path and is read-write and executable from another one. That seems like a terrible idea. So it becomes easier to manage one set of metadata if it's just in one location. Ooh, I have a question. Is there a reason why 11 isn't indexed right after 10, or does it not matter? Yeah, the reason why it wasn't indexed right after 10 is because of the example from a previous slide. I do want to go back to it just to make sure that I don't create confusion. It was this slide right here. I clicked, stop moving, PowerPoint. Talk about program usability. Let me try this one. Okay, so the idea was that these blocks were not actually in order, 3, 4, and then 10. And then, so block 10 and block 11 are both in the file, but the next logical block in the sequence is this one over here, 13, if I remember correctly. 13, 14, 15, and then back to 11. And so that's why in the file, the index. Oh, stop clicking. You are irritating the crap out of me, PowerPoint. Anyway, so that's the reason why 11 comes last, because I'm actually having the same logical sequence of blocks across all of these examples. So you can see how one file may translate in these different representations. Okay, let's try to get this wrapped up. The overhead here is the index. So, you try to balance different considerations when you do these, because you want a simple index for small files, and you want a sophisticated index for large files. Now, I'll tell you right now, the best answer in the universe is a B tree, but that's not what older Linux operating systems would do. And so we actually have something else that we do. I'm going to actually jump to this real quickly just to show you. We'll talk about it more next time. But what you would end up with is you'd have the metadata in the index block, and then you'd have a number of entries where you point directly to the blocks. And then if you got above a certain size, you start having this thing called a single indirect block, where you reference another index node that references more blocks. And then if you got beyond the sizes for that, then you would fall into a thing called a doubly indirect block. And so if you've heard of ext2, ext3, ext4, those were this kind of a layout. Modern operating systems, though, we tend to just use B trees, because B trees can handle all of this stuff super efficiently. And like I said, I love them. They're my favorite data structure in the universe. We're going over time. Let me see. There's a question here. Storage constraints. Why is the index block more effective than the file allocation table? The answer to that really gets back to the issue of clusters versus being able to allocate blocks to files on an individual basis. By having a global file allocation table, we have to hand out typically large chunks of storage, because the file allocation table quickly, it would just exceed the useful size of the device. And so instead of having one global file allocation table, why not just have a little file allocation table per file? And that allows you to continue referencing things on an individual block level instead of having to hand out large clusters. So it gets back to that reasoning. There's a few other details as well. File allocation table is linear and it doesn't support search operations, whereas these indexes are hierarchical. So you can do sort of binary search over them super efficiently. So those are the two big reasons. Okay, I'm going to wrap it now. I'll hang out if anybody has any further questions, but I will see you next time.